Good evening. Thank you very much for making time to join us. Welcome to today's class. Um, Let me start by apologizing for firstly, I think, sending the assignment late. I was supposed to have sent it on Saturday, but I only managed to send it on Saturday. So apologies for not communicating in time. Right. Then I think before we go any further, we are going to have, I think, now that the exam calendar is out, right? So I think we're anticipating that the exams are going to start in November, but seeing that they're starting in October, there's no need for us to revise our timetable a bit. Right. So I'm going to be in communication with you, I think, by end of before midnight tonight. You'll receive an email that will confirm the path forward. But more or less, it is going to be along the lines of having more classes. Right. So this will mean that we're going to have generally up to 3 classes a week in the next 2 weeks, and then after that we finish the content. From then on, we can then start with revision. Right? So what this means for you as a student now is the fact that you have to start practicing for the exam right now. So I understand the pressures of not being a full-time student, right? So you cannot really leave this for the last minute, and it really needs. So if you do a chapter with just practice questions, not to go full depth in it and as if you're writing tomorrow, but practice questions so that you get used to the notations, the concepts, the mistakes that one can make, and so forth. So I think that is very critical that you start doing right now, looking at past papers as well. So if it is going to be multiple choice, I'm not sure if it has been confirmed that it's going to be multiple choice or not. If it is going to be multiple choice, you need to practice extra hard, right? Because all the 4 options look correct, and then you need to discern, right? So they will be testing more of your understanding. If it is a structured paper, the better, because even when you are unsure, you still get part marks. So, and no, there are people who wrote last semester, and what they were complaining about is the moment that if it's something that you have no idea of, it's 10 marks gone from the multiple choice questions, because it was 10 questions and it was 100 marks. So it was essentially 10 marks per question. So that makes it very easy to pass and get high marks, or very difficult to pass, because there are no part marks in between. So if it is confirmed to be a multiple choice, then you need to practice extra harder and focus more on understanding why things work, right? And that is where I'll play a bigger role. So now going forward as well, I think in terms of communication, right? From my side, I know what needs to be improved, especially on the communication on Telegram and so forth, and instant feedback. So I can, I think, avail myself from every second day, say Monday, Wednesday, and Friday, from 10 o'clock. After I finish my classes this side, anything that will be pending will be resolved by then. So that is how we can work together going forward. I don't know if there are any questions from your side. Any questions from your side? Then on the issue of the premium videos, right, so it's still being resolved. Hopefully, if after our crash 2 weeks, then you then use them to practice whilst we are starting with the or you can always use them to refer back. So they're still gonna be there before I think we start our revision classes. All right. Now, I think in the last class we had looked at PDAs, right? We had looked at PDAs in the previous class, right? And then I asked you guys to go and do some questions. I don't know if you managed to go and do questions or not. Did you manage to go and do some questions, and did you come across any difficulties? Right. So we last looked at this question. Now let us look at this one over here. Right. So we are asked to build in our DPDA that accepts the following language: a to the power of n plus 1, b, a to the power of n minus 1, and bb. Right. So when you look at this language, firstly, number one, the first thing that you need to do is to understand how the dynamics of the language operate. Right. So this language that is in front of us is going to have n plus 1 and n minus 1 here. Right. So what does that mean? Physically, what does it mean? It means that we're going to have two more a's here than we are going to have there. Right. We're going to have two more a's on this clump of a's than we're going to have there. Because to move from n minus 1, if you add 1, you get n. If you add 1, you get n plus 1. So for you to move from n minus 1 to n plus 1, it's 1, 2 moves. All right. So those are that's what it physically means to say there are two more a's than in the first clump than in the second one. So in terms of building a PDA, we are also going to be tracking the n, right? So it means that this is going to go into the stack. We're going to push this into the stack, and we're going to pop this, use this to pop the stack. But already we've observed that we are going to have two more elements in the stack than we can use to pop out. So we need to find a way of dealing with that. So we can then start our machine. We start it, and then we go and we read. Right? So after we go and we read, we then we want to start with an A, and then if we read an A, we want to push into the stack. So we push, say, an X into the stack, and we go and we read again. If we continue reading A's, we're going to push an A into the stack up until we read a B. Right. So when we read a B, we're going to read again, and then we expect to read an A, at which point we pop the stack. So we're going to find in, we can say we pop an X, and then we read again. As long as we read A's, we pop the stack. So at some point, we are going to read an A and pop an X, and then we do not read a B at this point. We do not read an A, right? Because what I'm saying is we have got, say, 1, 2, 3, 4, 5, 6 A's, and they've got 1, 2, 3, 4 A's in the first clump. So this one is going to take out that one, this one is going to take out that one, this takes out this one, this takes out this one. So when we come in, we read. At this point, we're not going to find an A, but what do we find? We find a B. So this B can then come and take this one out. So this B can take this one out, and this B can take the last two out. So you're going to pop an X, and then you read a B. When you read this B, you want to pop the stack, you pop an X, and then you read a B again, and then you pop, right? So you have got one X out, read a B, you pop an X, that is the second X that is out. So you've taken this out, you've taken this out. They are now out. So after you do this, then you can now read. You have reached the end of the word. You're going to read it now, and then the stack should now be empty. You pop it now, and then you go to accept. Like that. Right. So that will be the machine. Now, earlier or last time I mentioned that you need to be very careful about the initial conditions. So what is the initial condition in this case? N is equals to 1. When n is equals to 1, we're going to have a to the power of 2b and then bb. Right? So what do? Is this weight going to be accepted by the machine? We have to make sure it is accepted. So you're going to have a, b, b, b. So I read an A and then I push an X into the stack. I read another A, I push an X into the stack. Then I read a B, right? And then after that, I read another B, this one. So I've got a path for reading a B at this point. So I read a B. That B, what does it do? I pop an X, so I take out the X. And then I've got another B over here. I read another B, the last B, and then I pop out an X, then I'm going to have nothing left in the stack. Then I read a null, I pop a null, then I go to accept. So this machine is catering for both the initial condition and the remainder of the words that are in the language. All right. Any questions there? Questions? Now, let us look at this one as well. L is equals to BA M N double A to the power of N BA to the power of N plus 1. Yeah. Can someone explain to me or try and tell me what are we keeping track of in this language? What exactly are we keeping track of in this language? Anyone wants to try? What are we keeping track of in this language? We've got two superscripts, M and N. Which one are we keeping track of? Which one is important to keep track of? Anyone? Which superscript are we interested in keeping track of? And why? Right. So we use a stack when we want to keep track of something. So M is not linked to anything else, right? But here you've got N linked to N plus 1. So those two are linked. So this B to the power of M does not have any correlation with N. Therefore, we are not keeping track of it. Right? So what we're going to do is we're going to build our PDA. We start, and then we're going to have read. We want to read the B, and then we want to read. These do not affect the stack a B, and then you also want to read, right? So if you continue reading a B, because you can do this, you can say, if you continue reading a B, you continue reading like this. It is not going to affect you. Generally want to put a loop there. Then otherwise, if you read an A, you want to read again. You want to read again. Right, so over here, I just need to correct something. M is greater than or equal to 1, so it's mandatory that you have at least 1. So you need to read at least 1B, and then when you read, you then can have a B substring that goes, a B loop that goes like that. Then we have an A, you read, you have another A. After this double A, you want to push something into the stack, so let's push a Y. Then you go and you read again. If you read a double A, how do you show that you read a double letter? You read an A, then you come, you read again, you read another A, then you push into the stack. So after that, you're going to, after reading an A, if you read a B, you exit this loop, and then you read again. You're going to read an A. This is supposed to allow you to pop the stack. Right, now before we proceed, I just want us to understand this language. So we've got a to the power of n, and we've got ba to the power of n plus 1. So we've got more elements that we can use to pop than the elements that are in the stack, right? So it means you're gonna read a b and a, then we pop the stack, and at some point you're gonna read a ba and the stack is supposed to be empty. And it was supposed to read the ba and the stack is supposed to be empty. So you want to pop, you can pop the stack. So you can pop an ay. But in the previous one, what I did is I did something like this. I popped in, if I pop a y like that. In this case, it's very dangerous for me to do because I've created a back loop that allows the path to say I pop a y, and then it allows me to read an a and read an a, read an a, read an a, continuously read a's, right? So in this particular case, I came back to this one directly because there was one way out of it, or it ended up being two ways. But in any case, it did not go back to areas that I had already passed. So you just have to be careful about that. You just have to be careful about that. So this is not gonna cut it. Yeah. So you have to get rid of that. Now, what I'll then do to cater for that is I'll go forward and create a unique read state. Now, if I were to read a B, I can come to this read with an A because I know it does not go back, it does not feed back into the system. Right. So I've got an A, a B, rather it's a B and an A and a pop, B and A and a pop. So at some point I'm going to read the last BA, the one additional BA, and then when I pop, it's not going to be a Y, but I'm going to pop a now, right? After which I read a now. If I read a now and I pop a now, I should be fine. I should go to accept, like that. Right. Again, the initial conditions in this case are working within our favor because n is equal to 1. Any questions? So Gladys, yes, Gladys, go ahead.
Can we revisit why we're not interested in M and we interested in N? Are we saying that if we had, for instance, BAB to the power M and then AA to the power N and BA, so maybe NAA to the power M plus 1 instead of N, M plus 1, and then BAN, for instance.
Gladys, can I stop you there? I think I lost you somewhere in the middle there. Can you try go again, just a little bit slowly this time? Yeah.
Okay, so what you said was we are interested in tracking N.
Yes.
Okay. Now my question is, how would one know in an exam that which one of the two, is it exponents, you are interested in? So if we had, for example, BABM, AAM for Mary plus 1, and BAN for Nelly, M plus 1, and then we had BBN or BAN, whatever, yeah.
Yes.
How would we then handle it? Would we be more interested in M? And if so, what is the reason?
All right. Is there anyone who wants to tackle that before I get into it? Any takers? Yeah. So if I can rephrase Gladys' question, she's asking to say, how do we decide what to keep track of? Right? How do we decide what to keep track of? Right. So Let me, I think, if I can make reference to the need of context-free languages, right? Initially, we had languages like A to the power of n, B to the power of n, and when we're looking at regular languages, we use pumping lemma to say, no, this language is not regular, right? So why was it not regular? We have got A clean star, B clean star, of which A to the power of n, B to the power of n is a subset of this language, right? But so A star, A clean star, B clean star can generate this language or words in this language. But we cannot have a specific regular expression for A to the power of n, B to the power of n. Right. So A to the power of n, B to the power of m, we can have a regular expression, which is this one. But A to the power of n, B to the power of n, we cannot have a regular expression. The reason was because of the nature of A to the power of n, B to the power of n, we have to keep track of saying how many A's are there and how many B's are there. Right. And that was the reason for introducing the stack. So to keep track, to say, I want to mark and say, I've done this. If I've done this, I put a placeholder. If I've done this, I put a placeholder. If I've done this, I put a placeholder. So that when I go, when I reach some point, I can then come and say, okay, I can match, I can do matching now to say, okay, this is taking this out, this is taking this out. And I can then have a check method of some nature to confirm that the ratio or the tracking that I'm doing is respected at the end of the day. Right. So that was the failure of regular languages. So when the question is, how do we know which ones to use? The short answer becomes, what are you tracking? What is it that you are tracking, or what is the language demanding that you track? Right. So that is the question. What is the language demanding that you track? Okay, in this specific question, if I were to track M, right, how, if I put this into the stack, how does it assist me in with this A and with this BA? Right. So the question to ask then is, what is being tracked in this question? Where is the restriction in this question? Right. So what is a restriction? A restriction can be M is greater than N, right? A restriction, if we've got B to the power of N, B to the power of N plus 1, or A to the power of N plus 1, we are saying the restriction is that the number of B's are, or the number of A's are greater than B's with 1, right? So that is the restriction that we have. So we want to identify that restriction, and that is the one that we're going to be tracking or using the stack for. So given any question in the exam or wherever, you're asking yourself, what is required for me to track? What is the restrictions imposed by the language? Right. So I don't know if that partially answers you or fully answers you.
I think it does.
Yeah.
Thank you.
So the exact signs of knowing, so now, because they can be really tricky or sneaky, and then say A to the power of N, B to the power of M, and then they can then come and say M is equals to N plus 1. Right.
Yeah.
So what this simply
So
means
then your
is
M, you
that,
replace it with N plus 1, right?
yes, it's
And
going
then
to
you
be
track
N plus
that
1.
B to the power N plus 1, right?
Exactly. So,
Yeah.
or if they were
Okay.
to say
I
A to the
get
power
you.
of N, B to the power of M, and they say M is greater than N, right? Or N is greater than M. Let me use N is greater than M. N is greater than M, like that. So if they were to say this, all they are saying is you are supposed to have more A's than B's. right? How do you then build
Then peace.
how do you then build a machine that accepts such a language? Right. When we are building these machines, what you see, if I take you a step back, is that at this point, at some point, right over here, after I read 2b, I took an x, a b, I took an x, and then I wanted to confirm that I'm at the end of the word number one, and number two, the stack is empty at the same time, because those were the initial conditions of the stack and of the tab. Right. So I'm imposing a checksum. But words or languages like this one will not require the imposition of a checksum. Why? Because I do not care by how much more A's I have, but I just need them to be more. So what does it mean? It means that if A's are going to be more than B's, right? If you are going to have more A's than B's, it means you are as long as you have something remaining in the stack, that rule has been followed. So after you popping, you are supposed to get to a point where you read a now, right? But when you go and pop, your stack should still have something, right? The moment you get to something, read a now, pop a now, it means that the elements that you were using to pop are less than the elements that were actually in the stack. Right? So now that is now something that is you are not going to read anyway, but you're going to realize as you build more of these languages. Right. So I think I may have gone overboard with the explanation, but I hope you are answered.
I am. Thank you so much.
Right. Anyone else with any questions so far? All right. So you are going to have this one, n plus 2, b8 to the power of n, right? So we have got more over here than we have over there. So we're going to get to the end of the word and we're still going to have two more elements in there. Right. So I'm gonna say start my machine, and then I'm going to have read, and then I'm going to have an AB, read, a B, then I read again, an A, then I read a B. So I just want you to see if you're following what I'm doing, right? I just want to see if you're following what I'm doing. So then I read an A, then I read a B, then I push an X, then I read. If I read an A and a B, I push an X. After that, I read a B and I read another B, right? And then I read a third B. After that, I read an A, and then I pop. What am I popping? I'm popping an X. Then I read again. If I continue reading a B, A, I continue popping, and then after that, I read a now. I pop a now. Then I go to accept. Right. Do you follow what I did to build this machine? Do you follow what I did to build this machine? Is there anyone who can explain what I did to build this machine? Any takers? In the event of a multiple choice, this will be a very critical tool for you to have, being able to interpret machines. Being able to interpret machines. Right. Yes, go ahead, ladies. Go ahead, ladies, yes.
Can I ask you a question first before I
Yeah.
attempt to explain?
Go ahead.
So we're only allowed to read one character at a time, right?
Correct.
So there's no way we would have read the AB or the BA or the BB.
There's no way you would have read a BB, yes.
Or an AB.
Yeah. So you need, if you are going to read an AB, you're going to read individually, read an A and read a B.
Read an A and then read a B.
Yes.
Okay.
Right.
So
yeah.
So because n is greater or equals to 1, I would ideally make my n a 1 initially, and then AB would be n plus 1, which is 3. So I'll do an A, B, and an AB, which is 3 times.
Yeah.
And then you do your BB, which is straightforward. And then because your n is 1, you would do 1B read, and then an A read. Huh? No. So for every B and every A that you read, you then, okay. So no, I'm lost.
Right.
Because then initially when we read your AB, which I assumed was to the power 3, weren't we supposed to then pop, not pop, but push for each and every character?
Right. So
Why
it's
do we go all the
allowed.
way though?
You don't have to push for every character, right? So remember,
Okay.
you are building the machine to the specifications, or you give the specifications of the machine. So you're saying, if you
Yeah.
do these two things, right, I'm going to give you this. So I'm saying, if I read an A and you read a B, then you're allowed to push an X. Right.
Oh, I see.
So you're not saying read an A, push an X, read a B, push an X. That's another way of doing it as well. You can also do that, but it is
It's
not
longer
optimal.
though.
It is not the best way to do it.
Yeah.
Right. I see there's
Okay.
a message from Gideon. You took the minimum case given to get the first 3 pairs of AB, right? Of course. So we are talking about AB, AB, AB. So you've got this AB, you've got that AB, you've got that AB, right? But it does not only read the minimum word, it reads all the words that are in the language. But do you understand why? That becomes the question. Elvis, you wanted to say something? Elvis?
No.
Right, what was your question? Right. So if you can see, okay, this is what I did. Let me try and break it down to you. So I acknowledge that my language has got how many more ABs than BAs? How many more ABs than BAs do I have? Right?
True.
I've got 2 more ABs than BAs. So what would you say if I then came to you and say, well, so what if the language is like this? Are these two languages the same? Would you say these two languages are the same?
Yes.
Right. So if these two languages are the same, it means I can read this AB without doing anything. That becomes this first AB. Then I can read this second AB without doing anything. That's this second AB. But then this AB that I read, it resides in a loop. So after I read this AB, I can now push, I interact with the stack, right? The moment I enter into the loop is when I start interacting with the stack. So I read an AB, then I push an X. I read an AB, I push an X. I read an AB, I push an X. So at the end of the day, I'm going to have n amount of X's in the stack. Then I read this BB, right, where I read a B and I read a B. Then I read a third B, right? So this third B over here is me introducing me to the second loop. So I read the BA and then I pop the stack, right? So at the end of the word, when I get to now over here, right, I've finished all the words that are on the tape. At the same time, if we are guaranteed of equality between the amount of elements in the stack and the amount of element BAs to clear the stack, then when I get to the end of the word, when I pop an X and I get to the end of the word, when I read now, the stack should instantly then be empty. Then I can go to accept. Yeah. I don't know if that makes sense. Well, does that make sense to you? If not, share your concerns. Right. So now this then goes to show you that there is no one way of building a PDA. There is no one way of building this machine. Right. I can think of two more ways that I could have built this machine, right, that accepts the same language as this one. Right. They are unique ways of, or there are different ways of building these machines, and you should not be restricted to one. Right. In the event that you are writing, I think you need to let me know as soon as possible whether you are writing a structured or a multiple choice question exam. Because if you are writing a structured, you can get used to doing one thing over and over again and you get comfortable with one method. But if you are writing a multiple choice, you are going to be looking at a machine that has been built by someone, and you're supposed to be able to detect, or you're supposed to be able to identify the language that that machine accepts. Or else you are going to be given a language and they're going to give you 4 options of PDAs for that specific language. Now, those 4 options may not be drawn based on what you are used to. So key is understanding or interpreting the machine correctly, the language correctly. So far, we've learned about how to move from the language to the machine. It is also important that you understand how to move from the machine to the language. Right. So I can say right now, I can give you the following question. Now I'm just going to draw a machine and I'm going to ask you to see if you can give me the language accepted. So I can say read an A, then read a B, then let's say I push an X over there, then I read an A, I read a B, and then at some point, if I say read a B, and then I read A,
Yeah,
I
hi,
want
how
to
are
say
you?
perhaps I want to pop, and then when I
Yeah,
pop an X, I want to continue reading. And then if I continue reading a B and then I read an A, then that will be fine. But when I pop an X, if I then if I read a now, right? If I were to just say, if I read it now, then I can have go to accept. What is this language? What is this language? What would this language be? So A, B to the power of n, B, A to the power of n? Nope. A, B to the power of 2 and B, A to the power, what's that, Victor? Is it? It's B, A to the power of? You're close,
Yeah.
Gideon, but not there. Close. So Victor, when you answer, there's something that's missing. Okay. Close enough? Not quite.
So you read a B. You read
Close
a
enough,
B,
but
you
not
read
quite.
an A.
So I can confidently tell you that the language A to the power A, B to the power of n, B, A to the power of n is accepted in this machine. But it is not the machine for that language. It is not the machine for that language. There's one critical piece of detail that's missing.
You read B, you read A, you pop X.
Whilst you're still contemplating, I want you to know as well that a machine can be wrong one of two different ways. Number one, if my machine accepts one additional word that is not in the language, then it is wrong. Number two, if my machine does not accept one word that is in the language, then it is also wrong. Right? So a machine is for a language if it accepts all the words, exact words, all of them that are in a language. Right? Not more, not less. Now, I want you to look at the following. A, B to the power of n plus 1, B, A to the power of n. Would this language get to accept? Would this language get to accept? So let's have A, B,
It should read
B, A.
It should read A, B.
So we read an A,
Read to
we read an
B,
A, we read a B, we push an
and
X.
then A,
We read an A,
pop,
we read a B, we push an X.
Read.
We read a B, we read an A, we pop an X.
Yeah.
We pop an X, right? So we are now sitting here. Right. What do we read? We have reached the end of the word, right?
Yeah.
So we read now. So if we read now, then we go to accept. So we are going to accept when we still have something that is in the stack. Right. So at bare minimum, it is going to accept the language A, B to the power of n, B, A to the power of n. But any other, the correlate language accepted will be something like this. So where m is greater than or equal to n. So I can have a language like A to the power of B, A, B to the power of n plus 100 and B, A to the power of n. This language is still going to be accepted. at bare minimum, right? At bare minimum, I'm supposed to have equal number of ABs as BAs, right? But others, or the other part of it, says that you can accept anywhere that has got more ABs than BA. It will be accepted. Right. So over here, the difference between this and what we're usually doing is that my checksum, I do not employ the usage of a checksum here. Because usually what you have seen me do up until now is I would come read now, and I pop a now, and then I go to accept. Right.
Yeah.
So, then there's a question from Gideon that says, can the machine accept when the stack is not empty, theoretically speaking? Even practically speaking, it can happen. Right? Even practically speaking, it can happen. Right. So let me use a very, very stupid analogy. Right. I can say, is it possible for you to stop eating whilst there's still food in your plate? Right? Can a person stop eating whilst there's still food in their plate? That can happen.
Yes.
So as long as the goal is achieved, it can happen. As long as the goal is achieved. Right. It could, but it will be a poorly designed machine. Right. So if you are building a machine, let me try and think of a machine. If you are building a machine, right? Usually when you are building a physical machine, you can be pedantic and design a machine for the task, right? That will be a very expensive machine than building a machine for tasks, right? That can do this task and more, right? Why is that machine that do a specific task expensive? Because that's all it can do, and if we need something to do something else, we have to start from scratch and do it, right? So it depends on what you are going for. In some cases, precision is everything, right? In some cases, precision is everything. If you are, say for example, you are doing medical surgical, you're a doctor and you're doing you're operating remotely on someone, you need to be or the parameters to be very, very precise, right? You cannot go a millimeter wrong, right? But if you are looking to, if you want to, you're building a missile guidance system, for example, it can be accurate to 5 meters, right? It can be accurate to 5 meters. It's still fine, because it will destroy the target that it is. So maybe it could even be accurate to 100 meters, because we know the target will be destroyed if it is accurate to 100 meters. So designing one that is accurate to 100 meters is actually cheaper than designing something that is accurate to 1 meter. Right. I don't know if that makes sense. So it becomes a matter of balancing, say, well, if it is out by 2, or what is the use case for this specific machine? Right. So yeah, I mean, there's a lot. You have got the Mars rover on the moon. What do you want it to do? You want it to be able to navigate and send pictures and so forth, and all that. But is it important to use? That's one of the worst cases, or not, maybe not the worst, but case studies of engineering. I don't know how much of engineering that you follow. So the first Mars rover, the one that is there right now, is not the first one that was supposed to go. The first one that was supposed to go, people designed it using I don't know if you're familiar with the imperial system. You designed the imperial system, but then it was operated by people who were using the metric system. So when you talk of 2, right? If I'm getting 2 meters and I'm talking of 2 inches or 2 centimeters and 2 inches, those are 2 different elements altogether. So the machine is telling you, well, no, look, you are close to the ground, but you are seeing on the scale that, well, you have only done 2 centimeters. I think, because the interchange is sort of something like inches and centimeters. So centimeters will be shorter, right? So you want to get to the ground and you're using centimeters. Inches, for you to get to 2 inches, you have to cover 5 centimeters. So the sensors will be telling you are too close to the ground, but you are saying I haven't traveled 2 centimeters yet, but the units are in inches. So that first Mars rover crashed, and that was millions, billions of dollars that went away. So accuracy is, well, plus or minus. If you're building a pizza delivery drone, you want it to go to the address that is there, right? If you are building a food aid drone, you want it to drop. It can drop at the nearest or wherever it could, close to the people. They will come and get the food. But if someone is paying for the food, you want to deliver it to the doorstep. But anyway, I can go on and on, but I think that paints the perspective. Right. So what's left now is for you guys to go and practice this a lot. I think I've given you the background or reason enough for you to go and start practicing. So you have to practice, number 1, to translate a language into the machine that it generates. After you finish drawing it, you test your machine with a couple of words that are accepted. Does it get to accept? And then you test your language with a couple of words that are not supposed to be accepted. Then you check whether or not it's getting to accept. If a word is not in the language and is still getting to accept, then you know that it is not, your machine is wrong. Right. Then number 2, you then need to look at any machine and then see which language is accepted. Because it's very easy for you to track these parts. When you are still here, it's very easy. A, B, push, A, B, push. But when you get towards accept, the conditions surrounding your acceptance are the ones that are important. Right? The conditions surrounding your acceptance are the ones that will tell you most times more about the language. So you can break down context-free languages into the following. You've got the first loop. So this one goes into the stack. Then you've got the second loop. This one takes element from the stack. From stack. These two need to be clearly identified. Right? These two need to be clearly identified. Then you have got elements that do not interact with the stack. So we have got elements that no interaction with stack. If it does not interact with the stack, no interaction with stack. If it is not interacting with the stack, what can you tell me about that? Right? We are not keeping track. So this part we are not keeping track. Right. And then at the end, we need a checksum. Right? A check digit or a checksum. Right. So before you start drawing your machine, you need to know exactly how you are gonna constitute your checksum. So if you have got 2 more in the stack than you have in the tape, you are supposed to then say, you read a null, you pop an X, you read a null, you pop an X, and then the third time you read a null, the stack will be empty, then you go to accept. Right? That is a checksum that you design before you even start drawing the machine, because you understand what the language is. Right? So these are the 4 critical elements of the context-free language. Right? How do you exit these loops and get to accept the checksum? How do you get into these loops? What are you getting, the first and the second loop? And then how are you dealing with elements that do not interact with the stack? And can you identify which elements are not interacting with the stack? Because this is something that we did in this specific case. Right? I identified the first 2 ABs as elements that are not necessarily a prerequisite, are not necessarily required to go into the stack for this machine to work. They could, we recognize them, but we just did not let them interact with the stack. Yeah. So in your day-to-day life, if someone says, if a random person meets you in the streets and say you're stupid, you probably will just brush it off. But if someone who holds value in your life comes and tells you that you're stupid, you're going to feel the difference between those same words said by 2 different people. So we are identifying what is important to the stack, what is going to affect the stack. That is what we're identifying, number 1. And then identifying what is not necessary or what is not important for the stack. And then lastly, how do you exit? How do you go to accept the checksum? Right. So let's stop there. I don't know if you have any questions that I'll gladly address. Any last minute questions? Right. So let's stop there. Then the next element that we're going to look at next time is going to be pumping lemma. Right. So it is a highly theoretical concept. So we are going to meet again this week. Either it's going to be tomorrow or Wednesday or Thursday. I'm just going to update the timetable. Then I'll send for you to it will be updated on the portal as well. But we're definitely going to meet 2 more times this week and 3 more times next week, so that we can cover a lot of the time that is no longer there. Right. Thank you very much for attending. Good night, and I'll see you again soon.